Can I ask you about some other weird particles that make up our universe?
Uh-huh.
What are axions? And what is the strong CP problem?
Okay. So uh, let me start with what the strong CP problem is. First of all, well, C is charge conjugation, which is the transformation, the notional transformation, if you like, that changes all particles into their antiparticles. And uh, the concept of C symmetry, charge conjugation symmetry, is that if you do that, you find the same laws would work. So the laws are symmetric if the behavior that particles exhibit is the same as the behavior you get with all their antiparticles. Then P is parity, which is also called spatial inversion. It's basically looking at a mirror universe and saying that the laws that are obeyed in a mirror universe, when you look at the mirror images, obey the same laws as the sources of their images. There's no way of telling left from right, for instance, that the laws don't distinguish between left and right. Now, in the mid 20th century, people discovered that both of those are not quite true. That really the equation that the mirror universe, the universe that you see in a mirror is not going to obey the same laws as the universe that we actually exhibit and interpret. You would be able to tell if you did the right kind of experiments which was the mirror and which was the real thing. Anyway,
So that's the parity, and they show that the
that's
parity doesn't necessarily hold.
It doesn't quite hold, and that in examining what the exceptions are turned out to lead to all kinds of insight about the nature of fundamental interactions, especially properties of neutrinos and the weak interaction. It's a long story, but it's
So you just define the C and the P, the conjugation, the charge conjugation.
Now that I've done that, I want to
what's the problem?
Shove them off.
Okay, great.
Because it's easier to talk about T, which is time reversal symmetry. We have very good reasons to think CPT is an accurate symmetry of nature. It's on the same level as relativity and quantum mechanics, basically. So that better be true.
So it's symmetric when you do conjugation, parity, and time.
And time and space reversal. If you do all three, then you get the same physical consequences. Now, but that means that CP is equivalent to T. But what's observed in the world is that T is not quite an accurate symmetry of nature either. So most phenomena at the fundamental level, so interactions among elementary particles and the basic gravitational interaction, if you ran them backwards in time, you'd get the same laws. So if, again, going back, unless this time we don't talk about a mirror, but we talk about a movie. If you take a movie and then run it backwards, that's the time reversal.
It's good to think about a mirror in time.
Yeah, it's like a mirror in time. If you run the movie backwards, it would look very strange if you were looking at complicated objects and a Charlie Chaplin movie or whatever. It would look very strange if you ran it backwards in time. But at the level of basic interactions, if you were able to look at the atoms and the quarks involved, they would obey the same laws. To a very good approximation, but not exactly.
Exactly. That means you could tell.
You could tell, but you'd have to do very, very subtle experiments at high energy accelerators to take a movie that looked different when you ran it backwards. This was a discovery by two great physicists named Jim Cronin and Val Fitch in the mid 1960s. Previous to that, over all the centuries of development of physics with all its precise laws, they did seem to have this gratuitous property that they look the same if you run the equations backwards. It's kind of an embarrassing property, actually, because life isn't like that. So empirical reality does not have this symmetry in any obvious way, and yet the laws did.
It's almost like the laws of physics are missing something fundamental about life, if it holds that property, right?
Well,
I mean, that's the embarrassing nature of it.
It's embarrassing. Well, people worked hard and at this is a problem that's thought to belong to the foundations of statistical mechanics or the foundations of thermodynamics, to understand how behavior, which is grossly not symmetric with respect to reversing the direction of time in large objects, how that can emerge from equations which are symmetric with respect to changing the direction of time to a very good approximation. And that's still an interesting endeavor. That's interesting. And actually, it's an exciting frontier of physics now to sort of explore the boundary between when that's true and when it's not true, when you get to smaller objects and exceptions like time crystals.
I definitely have to ask about time crystals in a second here. But
right,
so the CP problem and T, so there's flaws to all of these.
We're in danger of infinite regress, but we'll converge soon.
No, so it can't possibly be turtles all the way down. We're going to get to the bottom turtle.
So it became, so it got to be a real, I mean, it's a really puzzling thing. Why the laws should have this very odd property that we don't need, and in fact, it's kind of an embarrassment in addressing empirical reality. But it seemed to be exactly true for a long time, and then almost true, and in a way, almost true is more disturbing than exactly true, because exactly true, it could have been just a fundamental feature of the world, and at some level you just have to take it as it is. And if it's a beautiful, easily articulatable regularity, you could say that, okay, that's fine as a fundamental law of nature. But to say that it's approximately true but not exactly, that's weird. That's weird. So and then there was great progress in the late part of the 20th century in getting to an understanding of fundamental interactions in general that shed light on this issue. It turns out that the basic principles of relativity and quantum mechanics, plus the kind of high degree of symmetry that we found, the so-called gauge symmetry that characterizes the fundamental interactions. When you put all that together, it's a very, very constraining framework. And it has some indirect consequences because the possible interactions are so constrained. And one of the indirect consequences is that the possibilities for violating the symmetry between forwards and backwards in time are very limited. There are basically only two. Okay. And one of them occurs and leads to a very rich theory that explains the Cronin-Fitch experiment, and a lot of things that have been done subsequently has been used to make all kinds of successful predictions. So that's turned out to be a very rich interaction. It's esoteric, and the effects only show up at accelerators and are small and so on, but they might have been very important in the early universe and lead to them be connected to the asymmetry between matter and antimatter in the present universe. And so, but that's another digression. The point is that that was fine. That was a triumph to say that there was one possible kind of interaction that would violate time reversal symmetry, and sure enough, there it is. But the other kind doesn't occur. So we still got a problem. Why doesn't it occur? We're close to really finally understanding this profound, gratuitous feature of the world, that it's almost, but not quite symmetric under reversing the direction of time, but not quite there. And to understand that last bit is a challenging frontier of physics today. And we have a promising proposal for how it works, which is a kind of theory of evolution So there's this possible interaction, which we call a coupling, and there's a numerical quantity that tells us how strong that is.
Mhm.
And traditionally in physics, we think of these kinds of numerical quantities as constants of nature that you just have to put them in, right? From experiment, they have a certain value, and that's it. And who am I to question what God doing? They're just constant. Well, they seem to be just constants. But in this case, it's been fruitful to think and work out a theory where that strength of interaction is actually not a constant. It's a field. It's a fields are the fundamental ingredients of modern physics. Like there's an electron field, there's a photon field, which is also called the electromagnetic field. And so all of these particles are manifestations of different fields. And there could be a field, something that depends on space and time. So a dynamical entity instead of just a constant here. And if you do things in a nice way that's very symmetric, very much suggested aesthetically by the theory, by the theory we do have, then you find that you get a field which, as it evolves from the early universe, settles down to a value that's just right to make the laws very nearly exact, invariant, or symmetric with respect to reversal of
So it
time.
might appear as a constant, but it's actually a field that evolved over time.
It evolved over time. Okay. But when you examine this proposal in detail, you find that it hasn't quite settled down to exactly zero. It's still the field is still moving around a little bit, and because the motion is so the motion is so difficult, the material is so rigid, and this material that fills all the field that fills all space is so rigid. Even small amounts of motion can involve lots of energy, and that energy takes the form of particles. Fields that are in motion are always associated with particles, and those are the axions. And if you calculate how much energy is in these residual oscillations, this axion gas that fills all the universe, if this fundamental theory is correct, you get just the right amount to make the dark matter that astronomers want, and it has just the right properties. So I'd love to believe
that might be a thing that unlocks, might be the key to understanding dark matter.
Yeah, I'd like to think so. And many physicists are coming around to this point of view, which I've been a voice in the wilderness. I was a voice in the wilderness for a long time, but now it's become very popular, maybe even dominant in the...
So almost like, so this axion particle / field would be the thing that explains dark matter.
It would solve this fundamental question of why the laws are almost, but not quite exactly the same if you run them backwards in time. And then seemingly in a totally different conceptual universe, it would also give us an understanding of the dark matter. That's not what it was designed for, and the theory wasn't proposed with that in mind. Mm-hmm. But when you work out the equations, that's what you get.
That's always a good sign.
Yes.
Actually. I think I vaguely read somewhere that there may be early experimental validation of axion. Is that am I reading the wrong?
Well, there have been quite a few false alarms, and I think there are some of them still. I mean, people desperately want to find this thing, and but I don't think any of them are convincing at this point. But there are very ambitious experiments and you have to design new kinds of antennas that are capable of detecting these predicted particles, and it's very difficult. They interact very, very weakly. If it were easy, it would have been done already. But I think there's good hope that we can get down to the required sensitivity and actually test whether these ideas are right in coming years or maybe decades.
What is the effort of quantum gravity? What are the different efforts to have these two dance together effectively, to try to unify the standard model and general relativity, any kind of model of gravity?
Sort of the one fully consistent model that we have that reconciles that sort of tames gravity and reconciles it with quantum mechanics is string theory and its cousins. And we don't know what, or if in any sense string theory describes the world, the physical world, but we do know that it is a consistent reconciliation of quantum mechanics and general relativity, and moreover one which is able to incorporate particles and forces like the ones we see around us. So it hasn't been ruled out as an actual sort of unified theory of nature, but there also isn't in my view, some people would disagree with me, but there isn't a reasonable possibility that we would be able to do an experiment in the foreseeable future, which would be sort of a yes or no to string theory.
Okay, so you've been there from the early days of string theory. You've seen its developments. What are some interesting developments? What do you see as also the future of string theory? And what is string theory?
Well, the basic idea which emerged in the early 70s was that if you take the notion of a particle and you literally replace it by a little loop of string, that strings are sort of softer than particles.
What do you mean by softer?
Well, if you hit a particle, if there were a particle on this table, a big one, and you hit it, you might bruise yourself.
Sure.
But if there was a string on the table, you would probably just push it around. Mm-hmm. And the source of the infinities in quantum field theory is that when particles hit each other, it's a little bit of a jarring effect. And I've never described it this way before, but it's actually scientifically accurate. But if you throw strings at each other, it's a little more friendly. One thing I can't explain is how wonderfully precise the mathematics is that goes into describing string theory. We don't just wave our hands and throw strings around, and there's some very compelling mathematical equations that describe it. Now, what was realized in the early 70s is that if you replace particles by strings, these infinities go away, and you get a consistent theory of gravity without the infinities. Mm-hmm. And that may sound a little trivial, but at that point it had already been 15 years that people had been searching around for any kind of theory that could do this. And it was actually found kind of by accident. And there are a lot of accidental discoveries in this subject. Now, at the same time, it was believed then that string theory was an interesting sort of toy model for putting quantum mechanics and general relativity together on paper, but that it couldn't describe some of the very idiosyncratic phenomena that pertain to our own universe, in particular, the form of so-called parity violation. Our world
Ooh,
is,
another term for the bar later tonight.
yeah.
Parity violation. Okay.
So if you go to the bar and
I already got the renormalizable quantum
and you
field
look
theory.
in the mirror across the bar,
Yes.
the universe that you see in the mirror is not identical. You would be able to tell if you show
Which
the
one?
lady in the bar
Yeah.
a photograph that shows both the mirror and you.
There's a difference.
If she's smart enough, she'll be able to tell which one is the real world
Ooh,
and which one is you. Now, she would have to do some very precise measurements.
yes.
And if the photograph was too grainy, it might not be possible. But in
So
principle, it's possible.
Why is this interesting? Why is it? Does this mean that there's some not perfect determinism, or what does that mean? There's some uncertainty.
No, it's a very interesting feature of the real world that it isn't parity invariant. And string theory, it was thought, could not tolerate that. And then it was learned in the mid-'80s that not only could it tolerate that, but if you did things in the right way, you could construct a world involving strings that reconciled quantum mechanics and general relativity, which looked more or less like the world that we live in. And now, that isn't to say that string theory predicted our world. It just meant that it was consistent, that the hypothesis that string theory describes our world can't be ruled out from the get-go. And it is also the only proposal for a complete theory that would describe our world. Still, nobody will believe it until there's some kind of direct experiment. And I don't even believe it myself.
Sure, which is a good place to be mentally as a physicist, right?
Yeah.
Always. I mean, Einstein didn't believe his own equations, right, with the black hole. Okay,
Well, that one he was wrong about that. But he was wrong about that.
but you might be wrong too, right? So, do you think string theory is dead? If you were to bet all your money on
No,
the future of string theory,
I think it's a logical error to think that string theory is either right or wrong or dead or alive. What it is a stepping stone. And an analogy I like to draw is Yang-Mills theory, which I mentioned a few minutes ago in the context of Standard Model. Yang-Mills theory was discovered by Yang and Mills in the 50s, and they thought that the symmetry of Yang and Mills theory described the relationship between the proton and the neutron. That's why they invented it. That turned out to be completely wrong. It does, however, describe everything else in the Standard Model. And it had a kind of inevitability. And, they had some of the right pieces, but not the other ones.
sure.
And they didn't have it quite in the right context. And it had an inevitability to it, and it eventually sort of found its place. And it's also true of Einstein's theory of general relativity. He had the wrong version of it in 1914, and he was missing some pieces. And you wouldn't say that his early version was right or wrong. He'd understood the equivalence principle. He'd understood space-time curvature. He just didn't have everything. I mean, technically, you would have to say it was wrong. And technically, you would have to say Yang and Mills were wrong. And I guess in that sense, I would believe just odds are we always keep finding new wrinkles. Odds are we're going to find new wrinkles in string theory. And technically, what we call string theory now isn't quite right. But
We're always going to be wrong, but hopefully a little bit less wrong every time.
exactly. And I would, bet the farm, as they say.
Do you have a farm?
I say that much more seriously because not only do I have a farm, but we just renovated it. Before I renovated betting at the farm, my wife and I spent 5 years renovating it. Before
you were much looser with that statement, but now it really means something.
Now it really means something, and I would bet the farm on the guess that 100 years from now, string theory will be viewed as a stepping stone towards a greater understanding of nature. And it would, I mean, another thing that I didn't mention about string theory is, of course, we knew that it solved the infinities problem, and then we later learned that it also solved Hawking's puzzle about what's inside of a black hole. And you put in one assumption, you get 5 things out. Somehow you're doing something right. Probably not everything, but you're there's some good signposts, and there've been a lot of good signposts like that.
In your book, A Beautiful Question, you ask, does the world embody beautiful ideas? So the book is centered around this very interesting question. It's like Shakespeare. You can like dig in and read into all the different interpretations of this question. But at the high level, what to you is the connection between beauty of the world and physics of the world?
In a sense, we now have a lot of insight into what the laws are, the form they take, that allow us to understand matter in great depth and control it, as we've discussed. And it's an extraordinary thing how mathematically ideal those equations turn out to be. In the early days of Greek philosophy, Plato had this model of atoms built out of the 5 perfectly symmetrical Platonic solids. So there was somehow the idea that mathematical symmetry should govern the world. And we've out-Platoed Plato by far in modern physics, because we have symmetries that are much more extensive, much more powerful, that turn out to be the ingredients out of which we construct our theory of the world, and it works. And so that's certainly beautiful. So the idea of symmetry, which is a driving inspiration in much of human art, especially decorative art, like the Alhambra, or in wallpaper designs, or things you see around you everywhere, also turns out to be the dominant theme in modern fundamental physics, symmetry and its manifestations. The laws turn out to have these tremendous amounts of symmetry. You can change the symbols and move them around in different ways, and they still have the same consequences. So that's beautiful, and these things, these concepts that humans find appealing, also turn out to be the concepts that govern how the world actually works. And I don't think that's an accident. I think humans were evolved to be able to interact with the world in ways that are advantageous, and to learn from it. And so we are naturally evolved or designed to enjoy beauty and to symmetry, and the world has it, and that's why we resonate with it.
Well, it's interesting that the ideas of symmetry emerge at many levels of the hierarchy of the universe. So you're talking about particles, but it also is at the level of chemistry and biology, and the fact that our cognitive, sort of our perception system and whatever our cognition is, also finds it appealing, or somehow our sense of what is beautiful is grounded in this idea of symmetry, or the breaking of symmetry. Yeah. Symmetry is at the core of our conception of beauty, whether it's the breaking or the non-breaking of the symmetry. Yes. It makes you wonder why Why? Like,
Well,
so I
well,
come from Russia, and the question of Dostoevsky, he has said that beauty will save the world. Maybe as a physicist, you can tell me, what do you think he meant by that?
I don't know if it saves the world, but it does turn out to be a tremendous source of insight into the world when we uh, investigate kind of the most fundamental interactions, things that are hard to access because they occur at very short distances between a very special kinds of particles whose properties are only revealed at high energies. We don't have much to go on from everyday life, but so we have when we guess what the so we and the experiments are difficult to do, so you can't really follow a very wholly empirical procedure to sort of in the Baconian style figure out the laws kind of step by step just by accumulating a lot of data. What we actually do is guess, and the guesses are kind of aesthetic, really. What would be a nice description that's consistent with what we know, and then you try it out and see if it works, and by gosh, it does in many profound cases. So there's that, but there's another source of symmetry which I didn't talk so much about in A Beautiful Question, but does relate to your comments, and I think very much relates to the source of symmetry that we find in biology and in our heads, in our brain, which is that although it is discussed a bit in A Beautiful Question and also in Fundamentals, is that when you have symmetry is also a very important means of construction. So when you have, for instance, simple viruses that need to construct their coat, their protein coat, the coats often take the form of platonic solids. And the reason is that the viruses are really dumb and they only know how to do one thing. So they make a pentagon, then they make another pentagon, and they make another pentagon, and they all glue together in the same way. And that makes a very symmetrical object, sort of. So the rules of development, when you have simple rules and they work again and again, you get symmetrical patterns. That's kind of, in fact, it's a recipe also for generating fractals, the a kind of broccoli that has all this internal structure. And I wish I had a picture to show, but maybe people remember it from the supermarket, and you say, how did a vegetable get so intelligent to make such a beautiful object with all this fractal structure? And the secret is stupidity. You just do the same thing over and over again. And in our brains also, we start from single cells, and they reproduce, and they're each one does basically roughly the same thing. The program evolves in time, of course. Different modules get turned on and off. Different regions of the genetic code get turned on and off, but basically, a lot of the same things are going on, and they're simple things, and so you produce the same patterns over and over again, and that's a recipe for producing symmetry, because you're getting the same thing in many, many places. And if you look at, for instance, the beautiful drawings of Ramon y Cajal, the great neuroanatomist, who drew the structure of different organs like the hippocampus, you see it's very regular and very intricate, and it's symmetry in that sense. It's because it's many repeated units that you can take from one place to the other and see that they look more or less the same.
So you mentioned the infinity problem and the Hawking problem. Which Hawking problem? That the black hole destroys information, or which Hawking problem are we talking about?
Well, there's really two Hawking problems. They're very closely related. One is, how does the black hole store the information? And that is the one that we solved in some cases. So it's sort of like, your smartphone. How does it store its 64 gigabytes? Well, you rip the cover off and you count the chips, and there's 64 of them, each with a gigabyte, and there's 64 gigabytes. But that does not solve the problem of how you get information in and out of your smartphone. You have to understand a lot more about the Wi-Fi and the internet and the cellular, and
that's where Hawking radiation, this prediction, starts to come.
That's where Hawking radiation comes in, and that problem of how the information gets in and out. You couldn't have explained how information gets in and out of an iPhone without first explaining how it's stored in the first place.
Yeah. So just to clarify, the storage is on the plate,
on the plate,
on the holographic plate, and then it projects somehow inside the
bulk, the space-time is the hologram.
The hologram. But man, I mean, did you have an intuitive, when you sit late at night and you stare out at the stars, do you have an intuitive understanding of what a holographic plate is? Like that there's two-dimensional projections that store information?
How a black hole could store information on a holographic plate, I think we do understand in great mathematical detail and also intuitively. And it's very much like an ordinary hologram where you have a holographic plate and it contains all the information. You shine a light through it, and you get an image which looks three-dimensional.
Yeah, but why should there be a holographic plate? Like,
why should there be?
Yeah, why?
That is the great thing about being a theoretical physicist, is anybody can very quickly stump you with going to the next level of whys.
Yeah, like,
so
why
if you're
blue?
asking,
I can just keep asking. Yes.
Yeah, you could just keep asking, and it won't take you very long to. So the trick in being a theoretical physics is finding the questions that you can answer.
Sure.
So the questions that we think we might be able to answer now, and we've partially answered, is that there is a holographic explanation for certain kinds of things in string theory.
Sure.
We've answered that. Now we'd like to take what we've learned, and that's what I've mostly been doing for the last 15, 20 years. I haven't really been working so much on string theory proper. I've been sort of taking the lessons that we learned in string theory and trying to apply them to the real world, assuming only what we know for sure about the real world.
So on this topic, you co-authored a paper with Stephen Hawking called "Soft Hair on Black Holes."
Yes.
That makes the argument against Hawking's original prediction that black holes destroy information. Can you explain this paper?
Yes.
And the title.
Okay. So first of all, the hair on black holes is a word that was coined by the greatest phrase master in the history of physics, John Wheeler, invented the word black hole. Mm-hmm. And he also said that he made the statement that black holes have no hair. Mm-hmm. That is, every black hole in the universe is described just by its mass and spin. They can also rotate, as was later shown by Kerr. Mm-hmm. And this is very much unlike a star, right? Every star of the same mass is different in a multitude of different ways. Different chemical compositions, different motions of the individual molecules. Every star in the universe, even of the same mass, is different in many, many different ways. Black holes are all the same. And that means when you throw in Einstein's description of them, which we think must be corrected. And if you throw something into a black hole, it gets sucked in. And if you throw in a red book or a blue book, the black hole gets a little bigger, but there's no way within Einstein's theory of telling how they're different. And that was one of the assumptions that Hawking made in his 1974-75 papers, in which he concluded that black holes destroy information. You can throw encyclopedias, thesis defenses, the Library of Congress.
It doesn't matter. It's going to behave exactly the same uniform way.
Yeah. So what Hawking and I showed, and also Malcolm Perry, is that one has to be very careful about what happens at the boundary of the black hole. And this gets back to something I mentioned earlier about when two things which are related by a coordinate transformation are and are not equivalent. And what we showed is that they're very subtle imprints when you throw something into a black hole. There are very subtle imprints left on the horizon of the black hole, which you can read off at least partially what went in. And so this invalidates Stephen's original argument that the information is destroyed.
And that's the soft hair.
That's the soft hair, right. So, and soft is a word that is used in physics for things which have very low energy. And these things actually carry no energy. There are things in the universe which carry no energy.
In your book, Fundamentals, 10 Keys to Reality, I'd really recommend people read it. You you say that space and time are pretty big, or very big. How big are we talking about? Like what, can you tell a brief history of space and time?
It's easy to tell a brief history, but the details get very involved, of course. But one thing I like to say is that if you take a broad enough view, the history of the universe is simpler than the history of Sweden, say, because your standards are lower but just to make it quantitative, I'll just give a few highlights, and it's a little bit easier to talk about time. So let's start with that. The Big Bang occurred. We think the universe was much hotter and denser and more uniform about 13.8 billion years ago. That's what we call the Big Bang. And it's been expanding and cooling. The matter in it has been expanding and cooling ever since. So in a real sense, the universe is 13.8 billion years old. That's a big number, kind of hard to think about. A nice way to think about it, though, is to map it onto 1 year. So let's say the universe, it just linearly map the time intervals from 13.8 billion years onto 1 year. So the Big Bang then is on January 1st at 12 a.m. And you wait for quite a long time before the dinosaurs emerge. The dinosaurs emerge on Christmas, it turns out.
12 months, almost 12 months later.
Getting close to the end. Yes.
Getting close to the end.
And the extinction event that let the mammals and ultimately humans inherit the Earth from the dinosaurs occurred on December 30th. And all of human history is a small part of the last day. And so yes, so we're occupying only in a human lifetime is a very, very infinitesimal part of this interval of these gigantic cosmic reaches of time. And in space, we can tell a very similar story. In fact, it's convenient to think that the size of the universe is the distance that light can travel in 13.8 billion years. So it's 13.8 billion light years. That's how far you can see out. That's how far things can signals can reach us from, and that is a big distance because compared to that, the universe, the Earth is a fraction of a light second. So again, it's really, really big. And so we have, if we want to think about the universe as a whole in space and time, we really need a different kind of imagination. It's not something you can grasp in terms of psychological time in a useful way. You have to think, you have to use exponential notation and abstract concepts to really get any hold on these vast times and spaces. On the other hand, let me hasten to add that doesn't make us small or make the time that we have to us small, because again, looking at those pictures of what our minds are, in some sense, the components of our minds, these beautiful drawings of the cellular patterns inside the brain, you see that there are many, many, many processing units. And if you analyze how fast they operate, I tried to estimate how many thoughts a person can have in a lifetime. That's kind of a fuzzy question, but I'm very proud that I was able to define it pretty precisely. And it turns out we have time for billions of meaningful thoughts
in a
lifetime. So it's a lot. We shouldn't think of ourselves as terribly small, either in space or in time, because although we're small in those dimensions compared to the universe, we're large compared to meaningful units of processing information and being able to conceptualize and understand things.
Yeah, but 99% of those thoughts are probably food, sex, or internet related.
Well,
but
well, they're not. That's right.
Only like 0.1 is Nobel Prize winning ideas. But
that's true. But there's more to life than winning Nobel Prizes.
How did you do that calculation? Can you maybe break that apart a little bit, just kind of for fun, sort of an intuition of how we calculate the number of thoughts?
The number of thoughts, right? It's necessarily imprecise because a lot of things are going on in different ways. And what is a thought? But there are several things that point to more or less the same rate of being able to have meaningful thoughts. For instance, the one that I think is maybe the most penetrating is how fast we can process visual images. How do we do that? If you've ever watched old movies, you can see that when any movie, in fact, that a motion picture is really not a motion picture. It's a series of snapshots that are played one after the other. And it's because our brains also work that way. We take snapshots of the world, integrate over a certain time, and then go on to the next one. And then by post-processing, create the illusion of continuity and flow. We can deal with that. And if the flicker rate is too slow, then you start to see that it's a series of snapshots. And you can ask, what is the crossover? When does it change from being something that is matched to our processing speed versus too fast? And it turns out about 40 per second. And then if you take 40 per second as how fast we can process visual images, you get to several billions of thoughts. If you ask what are some of the fastest things that people can do, well, they can play video games, they can play the piano very fast if they're skilled at it, and again you get to similar units. Or how fast can people talk? You get to within a couple of orders of magnitude, you get more or less to the same idea. So So that's how you can say that there's billions of there's room for billions of meaningful thoughts.
Yep.
Now,
It'll
I
be
won't argue for exactly 2 billion versus 1.8 billion. It's not that kind of question, but I think any estimate that's reasonable will come out within, say, 100 billion and 100 million. So it's a lot.
it would be interesting to map out for an individual human being the landscape of thoughts that they've sort of traveled. If you think of thoughts as a set of trajectories, what that landscape looks like. I mean, I've been recently really thinking about this Richard Dawkins idea of memes, and just all this ideas and the evolution of ideas inside of one particular human mind, and how they're then changed and evolved by interaction with other human beings. It's interesting to think about. So if you think the number is billions, you think there's also social interaction. So these aren't
Yes.
like there's interaction in the same way you have interaction with particles. There's interaction between human thoughts that are perhaps that interaction in itself is fundamental to the process of thinking. Like without social interaction, we would be like stuck, like walking in a circle. We need
Yes.
the perturbation of other humans to create change and evolution.
Once you bring in concepts of interactions and correlations and relations, then you have what's called a combinatorial explosion, that the number of possibilities expands exponentially, technically, with the number of things you're considering, and it can easily, rapidly outstrip these billions of
Yep.
thoughts that we're talking about. So we definitely cannot, by brute force, master complex situations, or think of all the possibilities in a complex situations. I mean, even something as relatively simple as chess is still something that human beings can't comprehend completely. Even the best players still sometimes lose, and they consistently lose to computers these days. And in computer science, there's a concept of NP complete. So large classes of problems, when you scale them up beyond a few individuals, become intractable. And so that, in that sense, the world is inexhaustible.
And that makes it beautiful that we can make any laws that generalize efficiently and well, can compress all of that combinatorial complexity into just like a simple rule. That in itself is beautiful.
It's a happy situation, and I think that we can find general principles of the operating system that are comprehensible, simple, extremely powerful, and let us control things very well and ask profound questions. And on the other hand, that the world is going to be inexhaustible. that once we start asking about relationships and how they evolve and social interactions, and we'll never have a theory of everything in any meaningful sense, because
of everything. Truly everything is. Maybe we can sneak our way back from string theory into black holes.
Yeah.
What was the idea that you and Kamran Vafa developed with the holographic principle in string theory? What were you able to discover through string theory about black holes, or that connects us back to the reality of black holes?
Yeah. So that is a very interesting story. I was interested in black holes before I was interested in string theory. I was sort of a reluctant string theorist in the beginning. I thought I had to learn it because people were talking about it. But, once I studied it, I grew to love it. First, I did it in a sort of dutiful way. These people say they've claimed quantum gravity. I ought to read their papers at least. And then the more I read them, the more interested I got. And I began to see, they phrased it in a very clumsy way. The description of string theory was very clumsy and
mathematically clumsy, or just
mathematically
the interpretation?
clumsy.
Okay, got it.
It was all correct, but mathematically clumsy. But it often happens that in all kinds of branches of physics that people start working on it really hard, and they sort of dream about it and live it and breathe it, and they begin to see interrelationships, and they see a beauty that is really there. They're not deceived. They're really seeing something that exists, but if you just kind of look at it, you can't grasp it all in the beginning. And so our understanding of string theory in 1985 was almost all about weakly coupled waves of strings colliding and so on. We didn't know how to describe a big thing like a black hole in string theory. Of course, we could show that strings in theory in some limit reproduced Einstein's theory of general relativity and corrected it, but we couldn't do any better with black holes than before my work with Kuhlmann. We couldn't do any better than Einstein and Schwarzschild had done. Now, one of the puzzles, if you look at the Hawking's headstone and also Boltzmann's headstone, and you put them together, you get a formula for their really central equations in 20th century physics. I don't think there are many equations that made it to headstones. and they're really central equations, and you put them together and you get a formula for the number of gigabytes in a black hole. Now, in Schwarzschild's description, the black hole is literally a hole in space, and there's no place to store the gigabytes. And it's not too hard to, and this really was Wheeler and Bekenstein and Hawking, to come to the conclusion that if there isn't a sense in which a black hole can store some large number of gigabytes, that quantum mechanics and gravity can't be consistent.
We got to go there a little bit. So how is it possible when we say gigabytes that there's some information? So black holes can store information. How is this thing that sucks up all light and is supposed to basically be super homogeneous and boring? How is that actually able to store information? Where does it store information? On the inside, on the surface?
Yeah.
Where's?
Yeah.
And what's information? I'm liking this ask 5 questions to see which one you actually answer.
Oh, okay.
I'm
so
gonna
if
ask
you
you a
say
bunch
that, I should try to memorize them and answer each one in order, just to answer them.
No, I don't know. I don't know what I'm doing. I'm desperately trying to figure it out as we go along here.
So Einstein's black hole, the Schwarzschild black hole, they can't store information. Stuff goes in there and it just keeps flying, and it goes in the singularity and it's gone. However, Einstein's theory is not exact. It has corrections. And string theory tells you what those corrections are. And so you should be able to find some alternate way of describing the black hole that enables you to understand where the gigabytes are stored. So what Hawking and Bekenstein really did was they showed that physics is inconsistent unless a black hole can store a number of gigabytes proportional to its area divided by 4 times Newton's constant times Planck's constant.
And that's another wild idea. You said area, not volume.
Exactly. And that's the holographic principle.
The universe is so weird.
And that's the holographic principle.
That's called the holographic principle, that it's the area. We're just jumping around. What is the holographic principle? What does that mean? Is there some kind of weird projection going on? What the heck?
Well, I was just before I came here writing an introduction to a paper, and the first sentence was as yet imprecisely defined holographic principle. Blah, 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 blah.
Nice.
So nobody knows exactly what it is. But roughly speaking, it says just what we were alluding to, that really all the information that is in some volume of space-time can be stored on the boundary of that region.
So this is not just about black holes, it's about any area of space-time.
Any area of space. However, we've made sense of the holographic principle for black holes. We've made sense of the holographic principle for something which could be called anti-de Sitter space, which could be thought of as a giant, as a black hole turned into a whole universe. And we don't really understand how to talk about the holographic principle for either flat space, which we appear to live in, or asymptotically de Sitter space, which the astronomers tell us we actually live in as the universe continues to expand. So it's one of the huge problems in physics is to, apply or even formulate the holographic principle for more realistic. Well, black holes are realistic; we see them, but in more general context, to give a more general statement of the holographic principle.
If there's, other pockets of complexity, commonly called as alien intelligent civilizations out there.
Well, we don't know for sure, but I have a strong suspicion that the answer is yes, because the one case we do have at hand to study here on Earth, we sort of know what the conditions were that were helpful to life, the right kind of temperature, the right kind of star that maintains that temperature for a long time, the liquid environment of water. And once those conditions emerged on Earth, which was roughly 4.5 billion years ago, it wasn't very long before what we call life started to leave relics. So we can find forms of life, primitive forms of life that are almost as old as the Earth itself, in the sense that once the Earth was turned from a very hot boiling thing and cooled off into a solid mass with water, life emerged very, very quickly. So it seems that these general conditions for life are enough to make it happen relatively quickly. Now, the other lesson I think that one can draw from this one example. It's dangerous to draw lessons from one example, but that's all we've got. That the emergence of intelligent life is a different issue altogether. That took a long time and seems to have been pretty contingent. For a long time, well, for most of the history of life, it was single-celled things.
Yes.
Even multicellular life only rose about 600 million years ago, so much after. So and and then intelligence is kind of a luxury. If you think many more kinds of creatures have big stomachs than big brains, and in fact, most have no brains at all in any reasonable sense. And the dinosaurs ruled for a long time, and some of them were pretty smart, but they were at best bird brains, because birds came from the dinosaurs, and it could have stayed that way, and the emergence of humans was very contingent and kind of a very, very recent development on evolutionary timescales. And you can argue about the level of human intelligence, but it's, I think it's
Pretty impressive.
that's what we're talking about, and it's very impressive, and can ask these kinds of questions and discuss them intelligently. So I guess so this is a long-winded answer or justification of my feeling is that the conditions for life in some form are probably satisfied in many, many places around the universe, even within our galaxy. I'm not so sure about the emergence of intelligent life or the emergence of technological civilizations. That seems much more contingent and special, and it's conceivable to me that we're the only example in the galaxy, although, yeah, I don't know one way or the other. I have different opinions on different days of the week.
But one of the things that worries me in the spirit of being humble, that our particular kind of intelligence is not very special. So there's all kinds of different intelligences. And even more broadly, there could be many different kinds of life.
Yes.
So the basic definition, and I just had, I think somebody that Sarah Walker, I just had a very long conversation with her about even just the very basic question of trying to define what is life from a physics perspective.
Yeah.
Even that question within itself, I think one of the most fundamental questions in science and physics and everything is just trying to get some universal laws around the ideas of what is life, because that kind of unlocks a bunch of things around life, intelligence, consciousness, all those kinds of things.
I agree with you in a sense, but I think that's a dangerous question, because the answer can't be any more precise than the question, and the question, what is life, kind of assumes that we have a definition of life and that it's a natural phenomena that can be distinguished, but that really there are edge cases like viruses, and some people would like to say that electrons have consciousness, and so you can't, if you really have fuzzy concepts, it's very hard to reach precise kinds of scientific answers. But I think there's a very fruitful question that's adjacent to it, which has been pursued in different forms for quite a while, and is now becoming very sophisticated and reaching in new directions. And that is, what are the states of matter that are possible? So in high school or grade school, you learn about solids, liquids, and gases, but that really just scratches the surface of different ways that are distinguishable, that matter can form into macroscopically different meaningful patterns that we call phases of matter. And then there are precise definitions of what we mean by phases of matter, and that have been worked out and fruitful over the decades. And we're discovering new states of matter all the time, and kind of having to work at what we mean by matter. We're discovering the capabilities of matter to organize in interesting ways. And some of them, like liquid crystals, are important ingredients of life. Our cell membranes are liquid crystals, and that's very important to the way they work. Recently, there's been a development in where we're talking about states of matter that that are not static, but that have dynamics, that have characteristic patterns not only in space but in time. These are called time crystals, and that's been a development that's just in the last decade or so. It's really, really flourishing. And so, is there a state of matter or a group of states of matter that corresponds to life? Maybe, but the answer can't be any more definite than the question.
I mean, I got to push back on those are just words. I mean, I disagree with you. The question points to a direction. The answer might be able to be more precise in the question,
Well,
because just as you're saying, there's that we could be discovering certain characteristics and patterns that are associated with a certain type of matter, macroscopically speaking, and that we can then be able to post facto say, let's assign the word life to
yeah,
this
well,
kind of matter.
I agree with that completely. That's but that's so it's not a disagreement. It's very frequent in physics that, or in science, that words that are in common use get refined and reprocessed into scientific terms. That's happened for things like force and energy. And so in a way, we find out what the useful definition is, or symmetry, for instance. And the common usage may be quite different from the scientific usage, but the scientific usage is special and takes on a life of its own, and we find out what the useful version of it is, what the fruitful version of it is. So I do think, so in that spirit, I think if we can identify states of matter that, or linked states of matter that can carry on processes of self-reproduction and development, and information processing, we should say we might be tempted to classify those
As life.
things as life. Yeah.